Okay, welcome in everybody. Today we're looking at the third and final contribution to the van der Waals force, the London dispersion interaction. So this was worked out in the year 1930 by Mr. Fritz London, and he applied quantum electrodynamics to neutral atoms to see what would the interaction between them be. But this is a little bit more complicated than we want to do. It was similar to the perturbation theory we did in a previous video, but instead of that, let's look at the classical approach, which would be using the Bohr model for atoms. It's less accurate, but it can give us a better intuition of what's going on. So a key part of this model is this Bohr radius, A0, which is the smallest distance that the electron can be from the nucleus. It comes from relating the Coulomb energy to the kinetic energy electron, and it works out like this. H nu is going to be the energy of the electron, and E squared over 4 pi epsilon 0 we should recognize from our previous Coulomb energy. Now this happens to have a numerical value of about 0.53 angstrom, which is 10 to the minus 10 meter. And that's pretty accurate to what the radius of the hydrogen atom is, for example. So there's some merit to this theory. Now this h nu that we have in here, we can also write it, of course, as h bar omega. Both of these are in energy. And this numerically for the electron is about 2.2 times 10 to the minus 18 joules. So it's a small energy. It's quantized in nature. And we call this the I, or the first ionization potential. And this would be the energy needed to ionize the atom. If you think of this as sort of the energy with which this electron is bound, if you provide this much energy to the system with a photon, for example, carrying this much energy, it could drive off the electron. So that's one of the key properties of these atoms. So quantum mechanically, we know that if we have a positively charged nucleus, the location of the electron is really in the cloud. It's in sort of this smear around it, the distribution of which is given by the wave function. We'd solve the Schrödinger equation, and then we would perturb it to get the answer. But in the concept of the Bohr model, the electrons are a bit simpler. We say the electron's actually at a specific point, and it's simply in some kind of an orbit. Again, much like the planets orbiting around the sun. What this means is that at each point in time, we in fact have a dipole going between the nucleus and the electron, the magnitude of which is simply distance times charge. So the Bohr radius, A0, times the electric charge. And what we can do is simply plug this instantaneous dipole into our previous result, which was the Debye interaction energy, which would be what is the induction effect of having one dipole onto a second neutral atom. So just the Debye energy, which I'll call W sub D, just to remind you, was the magnitude of the dipole squared divided by the constant squared, r to the 6th, multiplied by the polarizability of the atoms. So just very simply, if we take this expression and plug it in, then we're most of the way there. But we have a few other results we can combine. The first of which is an old equation that maybe we didn't spend enough time on, but that we can estimate the alpha 0, the polarizability, to be approx these constants times the cube of the radius, So again, this radius would be the A0 constant. And we also had our previous definition for A0. So we got to make sure we're making this distinction. Alpha 0 is polarizability, A0 is the Bohr radius. So I'll just write that down again. This was E squared over 8 pi epsilon 0 h nu. So if we put both of these together, we can write down what this energy would be for the instantaneous dipole in this dispersion effect. So if we plug it all in, here's what we get. W of R, in this case for dispersion. I'm realizing now D could stand equally for Debye and dispersion. So maybe we'll call this WL for London dispersion. Would simply be minus alpha 0 squared times h nu divided by 4 pi epsilon 0 squared r to the 6. Now this is of course only approximately true. There's some numerical factor that's a bit off with this. How could we track down the more accurate numerical factor? Well, we'd have to do those quantum mechanical calculations, but that's what London did, so we can just quote his result. So London's actual result for the dispersion energy, so we'll put a proper equal sign here, is just what we found before, except it's a 3/4 in front. And then we write the same, but what we're going to do is we're going to replace h nu with I, because that's what we said was the ionization energy. That's a property you could look up for a particular atom, and we'll just write it in terms of that. Also with our constants, and of course the r to the 6 dependence. So that's really it. That's his result all the way back from 1930. What is that? 90 years ago? That's what he came up with. Now this would of course be for two identical atoms. So if we wanted to expand this for non-identical atoms, I'll write that underneath and hopefully we can see what that's going to be. We're going to have an alpha 0,1 and alpha 0,2. So that's just the polarization of each of the atoms. We're going to have this usual constants, the same r to the 6. And now we're basically going to have a new expression for I that depends on the ionization energy of either the two things. And this is kind of like a reduced mass, if you will. So we have the product of ionization potentials on the top, the sum on the bottom. So you see these are really the same, except the bottom, once again, is a little bit more general. But that's it. This is the third part of the trio, and in many ways this is the most important since it's always present. It doesn't rely on any dipole being present, it relies on more an instantaneous effect. Next time, we'll see how we can unify the three elements of the trio to have a more complete theory of the van der Waals force.